SwayamPrabha. Digital India. Educated India.
This is the same paper that generated many other works. So essentially you have a system like this, you have a double integrator, and you have this guy here. You see there is something that makes the system asymptotically stable if these were not there, right? But then there is this extra nonlinearity that you don't know what to do with it. So somehow you want to, the effect of this nonlinearity, you want to cancel it with the by designing a control input in the linear dynamics down there, right? So what you want to do is first design. Well, I will skip this. What you want to do is to design U to stabilize psi, but not only you want to stabilize psi, but also you want to add an extra feedback to take care of these terms here. Okay. So according to the theorem I showed you, what you do is the following. First, if this is just a double integrator, you first use a feedback to put the poles of your linear system in the right place. So let's say we choose these control gains to make the system down here asymptotically stable, and you add an extra input, as I said, to take care of these guys here. Okay, so this is the matrix that we saw before. So here A is just 0. What is it? 0, 1, 0, 0, right? And this guy here is A minus BK, yeah? Which I made it Hurwitz. Then there is the extra input. And my Lyapunov function that I'm going to use to figure out this input is going to be V, which is a Lyapunov function for the system x dot equals F0, which in this case is just x dot equals minus x cubed. So V equal x squared will do, right? Because with that you get V dot less or equal than well, actually equals to minus x cubed, right? If I consider V dot just to be the partial of V times F0. And what else? And then I have this guy here that will generate this one, and then I can figure out what I have to put in this input to take care of the extra nonlinearities that are sitting there in my system, right? And yeah, so I just do that computation. I take the derivative. This is minus Q, and this is C, and what else? Here I have psi, here I have psi, and V I can choose it, so I will just choose it to match exactly that, yeah, with a negative sign, and we'll take care of those nonlinearities. I will add a minus y here to add extra dissipation if I want, and then what will I obtain? I will obtain this. If I want to continue, maybe there is something that after this system I will go and interconnect it with something else. So let's just say, for the purpose of continuing think about passivity interconnections and so on, let's just invent a new input that I'm going to put in my system. So I close the loop, but then I add a new input. As you can see, I have passivity from this new input to the output y, because I have all these negative terms here. So I have actually strict passivity with respect to the state. Yeah, I have this negative term in psi, and I have this negative term in x. So that gives me strict passivity with respect to the state. And by adding this minus y here, I have a y square in this inequality, which gives me also. So this is integral of y square. it gives me also output strict passivity. So you see, with this controller, I enforced really the passivity of the system. So this is the picture I have. I have this system that I'm interconnecting with this one here. This system has as output this. So this is an output that I define. And I use that output to make the passive interconnection. So I'm going to use that output to inject it into this block. And I'm going to define this input V exactly as being that output. That's exactly what I just did, right? I said my new input V is defined by this guy here. Okay, so that's this. Then I take the output Y, and then it goes back into here. So as you see, yeah, it's for a particular class of systems, but yeah, often with mechanical systems and such, you can do that. So yeah, it looks like that because you have but essentially you. So think of this as, imagine you will give a lecture on adaptive control. So suppose you do your control knowing all the parameters of the system, and you know how to do that. And so you end up with this equation x dot equals f0, right? So that's the case in which you know the parameters. And then you don't know the parameters, so a bunch of extra things appear. Well, you can just take care of them with this feedback passivation term.
You started the example with saying there were cascades, and then you eventually do feedback.
Yeah, that's so this cascade story is that I skipped it because we don't have time. But Kokotovich was. I mean, this triggered all the study about cascaded systems, and as you can see, also this feedback passivation is exactly at the basis of feedback of backstepping, right? So, I mean, this paper really is at the basis of a lot of things. So the cascades thing is that you could imagine that if you have this system that is linear, that is perturbing your nonlinear system. An intuition would say, okay, I will just stabilize this guy, and once this is not there, I have a nonlinear system that is stable. So everything should be okay. So they remark that no, it's not like that in a nonlinear system, because if you like say I'm going to stabilize it like real fast, well, real fast for this system may also mean that you have a peaking in the transient, you have a huge peak, and then yeah, you stabilize it in 1 second. The psi is already very small, but this peak goes to certain levels, and if you inject more and more damping to stabilize it faster and faster, what you will end up with is that your system essentially will explode. The solution to the system up here is given by this equation. There shouldn't be x1, it's just x. So this is the solution to the system, and as you can see here, you have a bunch of terms with a -1 there. So at certain moment, all that cancels out. You are dividing by 0, and the solution explodes. So they were just remarking that, yeah, for these kind of systems, it's in cascade because this guy is completely decoupled. There is no dependence on x. If you just stabilize it with certain feedback, you make not only you will not be achieving stabilization also of x, but you will actually make it explode in finite time. So that's not what you should do. So they figured out, okay, so if the extra nonlinearities that are sitting there have certain structure, I can figure out how to inject some extra input here, in order to take care of those. But yeah, there are these structural properties, right? So you have to define certain output from your nonlinear system, and then you have to have that psi here appears in the nonlinearities in your system, but it doesn't appear just in any arbitrary manner. It appears like this. Remember, so you have to be able to factor out of your nonlinearities this y, which happens to be exactly c times psi. So and in this case, well, that output is this. Yeah. So. But then again, it's really about choosing the right output in your system to define this passivity property from the right output. And if you have these structural properties, you will be able to do things. Okay, I'll try to do this last part of the lecture on a specific kind of passivity-based control that is called energy shaping plus damping injection. You have probably heard of this. Yeah. So this method was originally proposed by a paper in '81, really long ago. That was also a very revolutionary paper because so '80s is I mean, it's really a long time ago. Basically, only Japanese had robots in factories and such. So back in those days, notably in chain production of cars, right? So basically, in those times, there was very little known about nonlinear systems. So they figured out how to control robots, robot manipulators, nonlinear systems, using this method that they called energy shaping. And it consists in, I was saying in the beginning, when you have a passive system, you have this energy balance equation. So what they figured out is, if I want to bring my pendulum to a desired position, all I have to do is manipulate the potential energy to bring the minimum of the potential energy to that position. And if through my control I am able to do that, I will be able to stabilize any equilibrium at that position. If on top I add damping, then I will also be able to stabilize it asymptotically, right? Using, again, the passivity notions. So just to illustrate this method, yeah, so you can also read about it in our book with Romeo Ortega in '98. But yeah, you know that this method goes back to these guys. So if I illustrate this method with a pendulum, what the situation we have is the following. This is the potential energy, the total energy of the pendulum, right? So kinetic energy and potential energy. And potential energy looks like this, right? So 1 minus mgl cosine. So it's that curve. As you can see, this energy has a bunch of minima. So we are thinking that Q is in R, okay? Don't think minus P, minus pi, but R. So if we think of Q in all variables in R, then it has a bunch of minima at n 2 pi n, right? Well, if you want to stabilize your pendulum at a specific point, you don't want all these minima. You want to first to have only one minimum, which is your equilibrium, and you want it to be global. So meaning that your potential energy should look more like a parabola or something. So what you want to do is to manipulate this potential energy. And you want to do that because, conserving the passivity properties and such. So the first thing to remark is that the pendulum, from the inputs u to the velocities, so as we already saw, torques to velocities, is a passive map, right? So if you take this function, the derivative will give you just the product of u times q dot if there is no friction. So it's a passive map, right? In other notation, it satisfies this. So in order to change the potential energy, the first thing you do is maybe add a line to the expression of the potential energy and also an offset. Okay, so first you want to put the minimum of your potential energy. You want to put it at q star somewhere. And if you add a line, then your potential energy now will look like this. So that would be 1 minus mgl plus an offset plus this line, right? So it will look like that. I still have several minima, right? But my system is still passive. All I did was just basically add this offset and this line here, and now my system will still be passive from a new input that I'm going to call UFB for U feedback. So there is a feed forward and there is a feedback. So the feed forward is just shifting the minimum of the potential energy to the gravitational vector to evaluated at Q star. Okay. Yeah, so that this system is passive, you can see it easily by just taking the derivative of the new Lyapunov function, the new storage function, the kinetic energy plus the potential energy of the pendulum, plus the modifications I added. So, of course, this function is 0 at Q equal to Q star, right? So these two guys will cancel out if Q is equal to Q star. Q tilde I'm defining as the difference, I guess it was somewhere in the other slides. Q tilde is the difference between it's here. So this will also go away. And so it has a singular point at Q tilde equal to 0. And actually that singular point is 0, so it's 0. If I take the derivative of that, as you can see, this guy goes away with this because it's multiplied there. This is 1. This goes away with that, and we only have left this guy here. So all I did so far is manipulate the potential energy, right? Now what I want to do is, I don't want the potential energy to look like that. I said I wanted it to be a minimum that is global, meaning that this point is smaller than any other point of the function, in the image of the function, and also it has to be the only one. Okay, global and unique is not the same thing. I could have a function that does, I don't know, it goes like this and then flat and then like that. So all these are global minima, right? So what I want is something more like what I have in this picture. And the way to achieve that is to add to what I already put in my function. I am going to add a parabola. So if you add a parabola to that, basically now the thing that was going like that, now it will look like this blue curve there. And but this blue curve for a certain value of Kp will look like this. And you can see there is another minimum there. Okay, so there is one minimum there and there is one minimum there. So this minimum is global, but it's not the only minimum in my function. There is also this one. So eventually my system could go and get stuck there. So I don't want that. So I increase my Kp to make my function rather look like this. Okay, so now I'm sure that I have a unique minimum. Once I have done that modification to my potential energy, I do that through the controller. So the controller essentially will carry all these extra terms that I need to modify the potential energy, and all that will cancel away. So we'll have this guy cancelled with it comes from this, so it cancels with this. This one comes from the controller, so it will cancel out with this one. Okay, so it's multiplied by Q dot here, and this one comes from the parabola that I added to my potential energy. That means that in my controller I should put this gain here. And it's a very simple controller for a nonlinear system, right? It's just a proportional feedback plus a constant essentially and cancellation of the nonlinearity, plus this compensation of the gravity at the equilibrium. With doing that, with doing this reshaping of the potential energy, what I'm doing is that I'm rendering passive. So in the beginning I had a passive system. Adding this offset only modified the minimum of the potential energy, but this system is still passive. And then I added this feedback here. So it's this proportional term. It's a feedback of Q dot if I pass it through an integral. So an integrator is a passive system, right? It's the simplest passive system you can think about. So x dot equals u, or let me write actually y dot equals u, v equals y squared. That means that v dot is equal to y times u. Passive system. An integrator is a passive system. So I have a passive system interconnected with a passive system. In closed loop, I will have a passive system, okay, which is expressed down there. And to make the new minimum, to make it global, what I need is to, as illustrated in this figure, I need Kp. So this is for a certain value of Kp rather small, and the red one is for an increased value of Kp. So actually the condition comes to Kp should be larger than the partial derivative of the gravity forces vector. And that will ensure me actually that the second derivative of V is positive, and that will ensure me that my function is strictly convex in Q tilde. Okay. This is only sufficient, it's not necessary. It doesn't have to be a parabola, it could be also a function that is a parabola only locally, but then it grows linearly. And then this condition will not hold, but for the purpose of energy shaping and all that, that still works. And then, yeah, so far what I have accomplished is I started with a passive system, modified the minimum. Applying this gain, I made sure that the minimum is global and unique. I still have a passive system there from every time I add a new input and towards the same output Q dot. And remember that theorem of Berns-Isidori-Willems. He was saying that if I have a passive system and I have that detectability assumption satisfied, all I have to do is to interconnect an extra feedback here, which is basically a function of the output with respect to which my system is passive. And this function here should be basically a nonlinearity living in the first third quadrant. Okay? So if I inject that, I will inject dissipativity in my system, and I will make the whole thing output strictly passive. So this block will be input strictly passive, but the whole block here will be output strictly passive. And yeah, so the proof of this proposition that we have with this controller global asymptotic stability can be done using this theorem that I show you, or Barbashin-Krasovsky, which probably you know wrongly as Lassalle's theorem, but it was actually originally proposed by some Russian guys several years before Lassalle. And the controller is right here. So it's what I just explained is the following. First, I added this, right, to change the minimum of the potential energy. Then we added this to make it global for sufficiently Kp large, sufficiently large Kp, and then this guy to add damping, right? So we call this damping injection, and with these two terms we call them energy shaping terms. And the proof is very simple. You just take as Lyapunov function the modified energy of the system. In this case, we only modify the potential energy. The derivative of all that is going to be it's going to be this, right? So you can see in UDI you just want to inject damping so that you get a quadratic term. I hope it is there somewhere. Yeah, here. You get a quadratic term in the output. Yeah, so this is the proof using Berns-Isidori-Willems. It says that all I have to do is inject this guy. That will give me V dot. With this, it will give me minus KD Q dot square. And then I have to check whether Q dot implies that Q goes to 0. In this case, actually, if I write Q dot equal to 0, that will go away. And I have this equal to 0. And the only solution of this equation is Q equal to Q star. And it is the only solution, once again, due to the condition that I'm imposing on Kp. So it has to do with making the only minimum to be K star. You can do the same proof using Lassalle again, so that you can write the system, or Barbashin-Krasovsky. You write the system in this form, go here, set x2 equal to 0 and see that the only solution that contained in this set is the origin, right? So, and the nice thing about this is that you have output strict passivity. So if you add another input here, you will have, instead of, in place of this, you will have the same input multiplied by q dot. So you could continue carrying on with more things. Let me just quickly show you what happens when you want to stabilize the system, again here. But remember, in the controller we were adding this term. It's the compensation of the gravity at q star. So this is constant. This is just a constant. Suppose you don't know that constant, so you want to estimate this constant. You put an estimate of the constant, and then you want to figure out how do I update this constant. Yeah. So it's typically what you do in adaptive control that you haven't seen that yet, but in this case it's just integral action, and it comes back to the method of Kokotovich. What we want to do is to first apply the control that we already know that works when we know the constant. And what we do next is we add and subtract that constant because we actually cannot put it there. So we are actually going to apply this controller. Okay. So we are going to use an estimate of that constant, and we add and subtract the real thing. Okay. So, but this is the control we're applying. This controller can be written like this. So the one that we already know how that it works, it gives in passivity, etc. Plus the difference between what I'm putting in and the real thing that I don't know. Okay, so that again is just well, this is constant and this is g hat. So I'm going to call that psi. So yeah, all this to say that the class of systems that fit this in this paper of Kokotovich is not that restrictive actually. For instance, here we have exactly that systems. Here we have this. This is the pendulum equation in closed loop. You can see here the kpq tilde term, right? This is the kd q dot term. And this is the gravity. This is the gravity. This is just g of q. And this is the compensation, the ideal compensation that I don't have. And when I apply the control with the estimate of the compensation, I will have these equations. So I have psi times a nonlinearity, which in this case is just this constant vector, right? And here we have this F0, remember, that has to be gas. But I know that it is gas because I know how to do things when I know the gravity compensation. So I say, well, how do I estimate G? Well, figuring out what to put in G dot, it comes to figuring out what I put in psi, right? So I basically just go ahead and write this equation, which is an extra integrated, and these guys would tell me, well, just put that. Well, I can't really because what? Because that would involve using psi in the feedback. If I wanted to put this term in this equation, it would involve using what I don't know. So I will just not put that. I will go ahead and test my chances with just the other part that takes care of the effect of this extra term that I have in my equation, and see what happens. So we didn't see that here, but there is a simple way to figure out a Lyapunov function for this guy. And using that Lyapunov function, you can establish passivity now, not only with respect to the velocities, but actually to this output, which is essentially a small constant times positions plus velocities. So it's just another passive map, okay? And when you apply that, you end up with this controller. So the controller you already knew how to that uses gravity compensation, but instead of gravity compensation, you use an estimate of it, and in place of the estimate, you put this guy, which comes really from the method of Kokotovich, which tells you, well, take the output of your system. If that output is multiplying this extra nonlinearity that you want to get rid of, well, just put that into your new feedback, and that will take care of this extra thing that you have in there. So you can see that by taking the derivative of this Lyapunov function with 1/2 of xi squared, you will see that you get this guy and this guy that comes from your equation here, right? So this and this go away, and then you get your system. And yeah, it all comes just to integral action. So this is what we had when we know the gravity term. If we don't know the gravity term, this passivity-based control is saying, well, just take this output, because the system is passive also with respect to this output, not just with respect to q dot. Take that output, pass it through an integrator, and then you will still be fine. And it all boils down to PID control. So you can see, so PID control for robot manipulators is another passivity-based controller. These are some references in case you want to know more about all this. Okay, thank you.